Welcome to section 2.1. The exciting things we're going to do today are matrix multiplication and transpose. Let's start with just basic matrix notation. You can describe an M by N matrix by denoting the columns. We usually use C's for the columns, or the rows, or each entry. And when you do each entry, A sub ij means the entry in the ith row, jth column. So in my example here, this is row 1, this would be column 3, and A sub 3, 1 would be negative 1. Third row, first column. All right, the zero matrix can be any size, and you take it to be the size that works in the context you're working in. The identity matrix has to be square. It has to be an n by n matrix. And the ones go down the main diagonal, meaning they start at the top left and go down to the bottom right. So the ones have to go in that pattern to get the identity matrix. All right, addition and scalar multiplication is done entry-wise. And I think it's easiest to show you what I mean with an example. I've got three matrices here at the top, and at first I'm going to add A and B. I'm going to add by adding each entry of A to the corresponding entry of B. So I'm going to add the 1 to the negative 1 to get 0. I'm going to add 2 to 2 to get 4. I'm going to add 3 to 1 to get 4. And moving down to the second row, we're going to get 1, 6, and 8. All right, the next one, I have 2c minus 3i. Now, c is given to me. I know that this I here has to be the 2 by 2 identity. Since c is 2 by 2, it only makes sense to subtract a 2 by 2 from another 2 by 2. You can only add and subtract matrices that they have the same dimensions. All right, and when you do scalar multiplication, for instance, 2 times c, this is c and this is I, you multiply every entry of c by 2. So that gives me 4, 2, negative 2, 6. And then I'll subtract, I multiply each entry of I by 3, so 3, 0, 0, 3. And that gives me 1, 2, negative 2, 3. Piece of cake. Okay, next one, can't do it. You can't take a 2 by 3 and add it to a 2 by 2 because they don't have the same dimensions. It's like mating a cow and a bunny. It's just not going to work. Rules of algebra. It's very straightforward. I'm just going to let you read through those on your own. Now let's talk about matrix multiplication. So this is the exciting part. Basically, you're going to be doing a bunch of dot products. When you multiply an m by n by an n by p, the important thing is that the inside dimensions have to match. The two ends have to be the same. When you do that, the resulting dimensions you're going to get by canceling out the inside dimensions and using the outside dimensions. So an m by n times an n by p will be an m by p. All right, rather than doing this general formula, I think it will be easier to show you what's going on by doing a specific example. So here I've got a 3 by 2, and I want to multiply by a 2 by 2. So the first thing you want to do is figure out your dimensions. So the 2's cancel, and I'm going to get a 3 by 2. 3 rows, 2 columns. Now the first column of my resulting matrix will be the matrix A times the first column of the matrix B. So just cross this column out for a minute and do the matrix multiplication. The first entry in the resulting product will be the yellow row dotted with the first column of B, which is 2, 3, and that gives me 2. The second entry of the first column will be the blue row dotted with 2, 3, and that gives me negative 7. And the third entry will be the red row dotted with 2, 3, and that gives me 3. All right, for the second column, I just ignore the first column of B and focus on the second column. So my first entry in the second column will be the yellow row dotted with negative 3, 1, which is 8. And then I'm going to dot blue row with negative 3, 1. That's negative 6. Make sure you follow those dot products. You can pause it and verify these numbers. And then the last entry, red row dot negative 3, 1, is 1. And so that's how you find a matrix product. Okay, here's another example. If A is 5 by 3 and AB is 5 by 7, what is B? All right, well, 5 by 3, and we're going to multiply by something to get a 5 by 7. Well, this matrix B has to have 3 rows because these 3's have to be the same. And if I'm going to get 7 columns in the end, this matrix B has to be a 3 by 7. All right, so pause the video and go and find these 3 matrix products. And the answers are on the last page, so you can check your work, but I don't want to proceed until you really understand how to find the product of 2 matrices. Okay, hopefully you did that. I'm not going to go through them all, but let's just look at the first one. We've got a 2 by 3 times a 3 by 2. So the dimensions of our product will be a 2 by 2. All right, and the first entry, top row, I'm going to dot this row with this column, and that's going to be 16. You should verify that. And then I'm going to dot this row with the same column, and I get -2. And then focusing in on the second column of the product, I'm going to ignore this column and focus on this column. So I'll take the dot product of the first row of A with that second column of B to get -1, and then second row of A with second column of B dot to get 2. Okay, matrix multiplication definition. This is not how you're going to multiply matrices in practice, but you should read through this on your own and just try and understand what it's saying. It's really stressing the fact that the columns of the product AB are linear combinations of the columns of A using the weights of B. And I did the exact same example that I did above at the top, but using the definition. You're going to get the same answer, but it takes a lot longer. So that's not how we want to multiply matrices in practice. All right, let's spend a little time talking about the properties of matrix multiplication. Matrix multiplication is associative, and it's distributive on the left and on the right. Now, normally we don't have 2 distributive laws. It would just be left distributive. However, matrix multiplication is not commutative. So we do need to state 2 separate properties for distribution. Scalars can go anywhere. They can go outside of the product, they can go with A, or they can go with B. And then this one's interesting. The identity times A is A, but what are the dimensions of that identity? If A is M by N, then in order to get A back, when we multiply by a square matrix here, it's got to be the M by M identity. And alternatively, if we multiply by I on the right, if this is M by N, it's got to be the N by N identity in order to get A back. So let me just show you a quick example. If A is 1, 2, 3, 4, 5, 6, and we want to multiply on the on the right by an identity matrix to get A back again, since A is 3 by 2, this would have to be the 2 by 2 identity, 1, 0, 0, 1. And you should verify that when you multiply those 2 matrices, you do indeed get A back again. Okay, and the exciting things about multiplication are the properties that it doesn't have. It's not commutative. There's no cancellation property. If you have AB equals AC, that does not imply B equals C. You can't cancel the A's like you could with multiplication of integers. Also, the zero factor property doesn't hold. If you take the product of 2 matrices and you get the zero matrix, that doesn't necessarily mean one of the matrices A or B was 0. And so those are super interesting properties. And we'll look at some of those in class. Matrix transpose. The transpose of an M by N matrix is M by N, and you just swap the columns and rows. So for example, if A is 2 by 3, then A transpose is going to be 3 by 2. What I do is I take the rows of A and turn them into the columns of A transpose. So the first row becomes the first column, and the second row becomes the second column. Okay, the next one, the transpose of a 2 by 2 is also a 2 by 2. This 5, 1 becomes the first column, and this 3, -2 becomes the second column. All right, the next one is a 2 by 1. this turns into a 1 by 2 that looks like this, 1, 5. And a 1 by 1 transpose is itself. So the transpose of 5 is 5. All right, properties of transpose. If you transpose and then retranspose, you get your matrix A back again. That makes sense. Transpose distributes over addition. And then property C tells you how scalar multiplication and transpose interact. The interesting one is property D. AB transpose is B transpose A transpose. Notice that the order flips, and that's important. So, for example, if A is 3 by 5 and B is 5 by 7, then AB is 3 by 7. So AB transpose must be a 7 by 3 matrix. All right, well, let's look at B transpose A transpose. B transpose is 7 by 5. A transpose is 5 by 3. So notice the dimensions work. I can cancel those 5s, and I get B transpose A transpose is 7 by 3. So the dimensions match up. Okay, that doesn't prove that AB transpose is B transpose A transpose, but it shows you how the dimensions work. All right, and that is the end of this section.